Hello, and welcome to the third video of the M2 chapter, Work and Energy. Quick starter question on the screen. Pause the video now if you've got time to do this. A package of mass 3 kilograms slides 4 meters down a line of greatest slope of a smooth, inclined plane, 30 degrees. Calculate the potential energy lost by the package. So we've got the mass is equal to 3 kilograms. And it is going to slide down 4 meters. Now remember, the vertical height is what we need here for potential energy, not the height down the plane. So for the vertical height, we need to create our right angled triangle here to calculate h here. Of course, this is still 30, so we've got h is equal to 4 sine 30 degrees, and the potential energy lost is equal to mass times the gravitational constant times the change in height. 3 times 9.8 times 4 sine 30, 58.8 joules of energy lost. In this video, we are going to look at conservation of energy and the work energy principle. So in a closed system, the total amount of energy remains constant. If you've done physics, you know that energy cannot be created or destroyed, and a closed system means that we're not putting energy in and we're not taking energy out. So if we're not putting any in and we're not taking any out, it can't be created, it can't be destroyed. The amount of energy must be constant. This is the principle of conservation of mechanical energy. Now, more formally, we say when no external forces other than gravity do work on a particle during its motion, the sum of the particle's kinetic energy and potential energy, the two that we're looking at in mechanical energy, remains constant. So in a very simple setup, for example, a box sliding down a plane where there's no friction because that would be an external force, and there's no pushing or pulling force because they would be external forces as well. If there's just gravity on a smooth plane pulling the box down, the particle's kinetic energy that it gains by sliding down must be coming from the potential energy it's losing, like we saw in the starter question, as it comes down the plane. And the amount must be the same. The amount of energy gained in kinetic energy must equal the amount of potential energy lost, and vice versa if it's going up the plane with a certain speed. Now let's be clear, this is for a closed system. However, closed systems aren't very realistic. Here on Earth, we tend to have a lot of friction, even if it's just air resistance. So we need to consider what happens if it's not a closed system. If there are external forces acting on a particle, for example a driving force or friction, they do work, and so they either add or subtract energy from the system. A driving force is probably going to add energy into your system. Friction is going to subtract energy from your system. This is called the work-energy principle, because the amount of energy you're getting or losing from the system is tied to the amount of work done by the forces, or against the forces. For example, against friction means you're losing energy, or work done by a driving force means you're gaining energy. More formally, the change in the total energy of a particle is equal to the work done on the particle. And we saw a simpler version of this in the previous video, where we saw that the change in kinetic energy is equal to work done on a particle. This time, we're generalizing it to include kinetic energy and potential energy, because as you're putting energy into the system, it's not necessarily gaining kinetic energy if instead it's gaining potential energy. These are the key ideas for the video. The rest of the video is looking at some examples. First one, a smooth plane is inclined at 30 degrees to the horizontal. A particle of mass 0.5 kilograms slides down a line of greatest slope of the plane. The particle starts from rest at A, call this point A, starts at rest, and passes point B, let's call this point B down here, with a speed of 6 meters per second. find the distance AB. A quick side note about exam questions. If you've got an exam question like this, it's very important that you take note about whether or not it's restricting which method you can use. Because you might look at this and go, oh, I can use constant acceleration to do this. But if the question says by considering energy, then you must use an energy approach, which is what we're going to do in this example. So here I'm going to focus first of all at point A and consider the energy at point A. The kinetic energy is pretty easy because there is zero speed, so there is zero kinetic energy. That has come from half times the mass times zero speed squared. The potential energy, I've got to be a little bit careful here to make sure that I choose a zero level for my height. So I'm going to choose the zero level that goes through point B so that the potential energy at point B will be zero. That'll be very easy. So this is my zero level. So compared with this level, I need to know this distance, which I'll call h. To do that, without knowing AB, I'm going to call AB x. Therefore, h is equal to x sine of 30 degrees. Sine of 30 degrees is a half. So the potential energy at A compared with the zero level is equal to the mass, 0.5, times g, which I will leave as g for now, because I don't know what x is anyway yet, so I'm not going to be able to get a final numerical answer out of this, times x over 2, and that gives me gx over 4. Now the reason for doing this is to find the total energy of the system. This is very important because this is the thing that stays constant or is added to or subtracted from by external forces. So we've got zero kinetic energy, gx over 4 potential energy gives us the total energy of the system at A, gx over 4. So when the particle is here, this is how much energy there is in the system. Now we know that there are no external forces other than gravity, because it's a smooth plane, so there's no friction taking energy out of the system, and there's no external force like a push or a pull putting energy into the system. That means by the time the particle gets to point B, this total energy of the system is still gx over 4. And we can work out the potential energy, because we put our zero level here, so the potential energy will be 0. So the kinetic energy at B must equal this amount. All of this energy has been turned into kinetic energy at that point. So now as I consider point B, we know the total energy must be the same, gx over 4. Nothing's been taken out of the system, nothing's been put in. And we know the potential energy is 0 because we've got mass times g times 0 height compared with my 0 height level, and the kinetic energy is equal to a half mv squared. We know v is 6, we know mass is a half, so that's a half times 6 squared is equal to 9. So the total energy in the system we know is gx over 4, but we also now know that the total energy in the system is 9 joules. So putting those two together, we can say that gx over 4, the total energy in the system, must equal 9. That gives me 36 over g. And now, if I want to, I can put 9.8 in for g and get a final numerical answer of 3.67 ... to two significant figures then, 3.7 meters as the distance AB. Second example. A particle of mass 2 kilograms is projected with speed 8 meters per second up a line of greatest slope of a rough plane inclined at 45 degrees to the horizontal. So we've got 45 degrees there. We have a mass 2 kilograms being projected up the slope with an initial speed of 8 meters per second. We know there is friction, And we're told in the next sentence the coefficient of friction between the particle and the plane is 0.4. Calculate the distance the particle travels up the plane before coming to instantaneous rest. So it's quite similar in what it's asking. It's asking for the distance here to here. And again, you might start thinking, I can use constant acceleration and friction and gravity and things like that, but we're doing this from an energy point of view, so I'm going to do something very similar. I'm going to look at our start point, consider the total energy of the system, and then look at the friction, the amount of work done against friction, take that away because that's being taken out of the system, and then whatever I've got left must have been converted into potential energy by the time the kinetic energy is 0. And that will tell me how far up I have moved here, call that h for now, and then I can work backwards with my little right angle triangle here to find out the distance that I'll call x again here. So I'll call this the start. At the start we've got potential energy. Again, I need to choose my level here, and to make it easy for myself I'll choose the level where it starts as my 0 point. So compared with this level, it has 0 potential energy, and its kinetic energy is equal to 1/2 times the mass times the speed squared, which is 64 joules of energy, plus the potential energy gives me a total amount of energy in the system of 64 joules. Now, during the movement, it is losing energy from the system because it's doing work against friction. So energy is being lost. So I need to know how much work is being done here, how much energy is being taken out of the system. So I need to know the work done against friction. To do that, of course, I need to know the force friction. And we know friction, if it's moving, is maximum friction mu times r, which is 0.4 times the normal reaction, this way here, which in this case is equal to 2g cosine 45. If I keep the g in there for now to keep it nice and exact while I work, that is 2g root 2 over 5. We know work done against friction is equal to force times distance, so friction times x, the distance in the direction of the force parallel to the plane. So that's 2gx root 2 over 5. Now we come to the end. At this point I'm going to need to know the height compared with the 0 level, so that is x sine 45, which is x root 2 over 2, which I'm going to need for the potential energy. But before I do that, let's consider the total energy in the system now. We started with 64 joules of energy here. We lost this many joules of energy during the motion due to friction. So at the end, our total energy is now 64 minus 2gx root 2 over 5. We also know at the end the kinetic energy, because it's got 0 speed, it comes to instantaneous rest, so the kinetic energy is 0, which means all of this must be converted into potential energy. All the energy that's left is potential energy. And the potential energy, which we know is mass times gravity times height, x root 2 over 2, must also equal this amount here, 64 minus 2gx root 2 over 5. So on the left we've got 2gx root 2 over 2, and then if we bring this over and we add 2gx root 2 over 5, gives us 7gx root 2 over 5 is equal to 64, and a final value for x, 3.298 ... or 3.3 meters to two significant figures. So just to recap the overall idea here, we looked at the total energy at the start, saw that work was done against friction during the motion, so this energy had to be taken away from the total energy in the system to give us the amount of energy that was left at the end of the motion, and at that point we knew that all of this was going to be potential energy, so we could equate the potential energy to the total energy that was left to work out x. Final example. A skier moving downhill passes point A on a ski run at 6 meters a second. After descending 50 meters vertically, the run begins to ascend. That kind of makes it sound like she's dropped off a cliff, descending 50 meters vertically, but I think we're supposed to assume that it looks kind of like this, and she's going down, and eventually, compared with her starting point, she's gone down 50 meters before it then starts to ascend, and it ascends some way kind of like this, up 25 meters vertically to point B. And these we would measure from this level here and call this our h equals 0 level. Okay, back to the key information here. She's going at 6 meters a second at point A, so that's her starting speed. By the time she gets to point B, her speed is 4 meters per second. The skier and her skis together have a combined mass of 55 kilograms. The total distance she travels from A to B is 1400 meters. So that is obviously this distance here as she goes along. Clearly not to scale. This is 1400 meters in red. The non-gravitational resistances to motion are constant and have a total magnitude of 12 newtons. So the friction, we're just told outright, is a constant 12 newtons the whole way. Calculate the work done by the skier. Okay, there's a lot of English there. There are a lot of easy places to get confused, but overall we're going to do the same method as before. We're going to look at the start point, consider the total energy in the system by finding her kinetic energy and her potential energy compared with this 0 level here. Then we're going to look at how much she loses due to friction along here, how much she has at the end, and then compare and see how much she must have done putting energy into the system in order to have however much energy we find she has here. So a similar idea to the previous question. At point A, we know she's got kinetic energy, a half times mass times speed squared, which is 990 joules. Compared with our chosen 0 level, she's got potential energy of mass times gravity times the height, 2750 G joules of potential energy. So the total is 990 plus 2750 G. During the motion, energy is being lost due to friction. We calculate how much that is by considering the work done against friction. And that is force times distance. We know that's 12 newtons times the distance travelled, 1400 meters. And that is 16,800 joules of energy lost because of friction. At this point, simply because of what the question is asking, we know that the skier is also doing work to put energy into the system. It's not clear from the rest of the question that the skier is doing anything to help herself move along, but because of the question, we can see that she must be doing work. Otherwise, they wouldn't ask us to calculate it. And that will go here. But just to emphasize that that must be something, I'm going to do the end first, because we know everything about the end. We know the potential energy and the kinetic energy. So let's do the endpoint B. The kinetic energy is equal to 1/2 times the mass times the speed squared. That's 440 joules. The potential energy compared with the zero level is mass times gravity times the height, 1375 g. So the total energy at the end is 440 plus 1375 g joules. And if I very quickly put these numbers in with a 9.8, this is 13,915. This one over here is 27,940. And you can see that if you take this number and subtract 16,800 joules, you do not get this number here. What you would get is 11,140. So we can see that something else must be going on, because at the moment we've said the total energy she starts with is this. She loses this amount of energy due to friction, and she finishes with more energy than she should. That means she must be putting in work. So the work done by the skier, call that x for a second, is found by doing this minus this plus this must equal this. Starting energy, take away energy lost due to friction, add energy put in by work done by the skier, must equal the total energy at the end. Seeing as we're about to work that out, I will use these numbers with the 9.8 put in, and we get 27940 minus energy lost due to friction plus energy gained due to the work by the skier must equal the final energy 13915, which means x is equal to 2,775 joules of work. Or what I should have done really is round it to two significant figures and say 2,800 joules. I hope that's been clear, and I hope that is enough for you now to have a go at some of the questions in exercise 4C. And maybe I'll see you for the final video in this chapter, all about power.